Cool. Hey, everyone. My talk is about scale and really the benefits of not having any. And again, like a bunch of other talks this conference, it links into a lot everyone else has said. But in general, this conference has been pretty good, right? I think ScaleConf is a good conference. Would you say so? I'd love to take a moment to thank the organizers and to point out one interesting detail about ScaleConf. As far as conferences go, ScaleConf hasn't really scaled. It's been around since 2012. It had a brief bump in 2015, but since then, it's been about 400 people every single year. And this isn't really a bad thing at all. It's a great conference. They're enabled to keep it this way because of their decision to not keep making it bigger. Specifically, conferences are a little bit different from tech companies, and I'm not going to talk in detail about why you want to keep a conference small, but rather focus on why, as a tech company, you can move quicker than the giant tech companies out there, the behemoths, and the advantages of being a startup. And really, for me, the prime benefit is about how fast you can move. And as an engineer, I really care about how fast I can code and how much product we can deliver to our end users at the end of the day. So this talk, in a summary, I'm going to talk a little bit about what I'm talking about when I say speed of development, a little bit about how to stay fast as a startup, and then finally some stories about decisions I've made and decisions we've seen in my previous companies that kind of reiterate these points. And then hopefully at the end of all of this, you can profit a little bit out of this knowledge. So before I get started, who am I? I'm originally South African. I moved to Silicon Valley about 6 years ago, San Francisco. It's exactly the same as the TV show, especially if you're working in the startup world out there. While I was in South Africa, living in Cape Town, I started a co-working space called CodeBridge, as well as a company called Snapbill, which offered billing services, software as a service, scaling from small businesses to insurance companies. Moving to San Francisco, I was working at Facebook, primarily on the Instagram team. I worked on their core infrastructure and developer efficiency, trying to get the engineers to ship code faster. At that time, we had about 30 people on the backend team and hundreds of millions of users. And I helped them ship their continuous deployment system, as well as migrate between data centers. And finally, I was the co-founder and CTO at a company called Smyte, startup. We were a huge scale, but we processed events coming in from social networks and marketplaces looking for abuse. So that's bullying, spam, fraud, harassment, whatever kind of bad stuff goes on the internet, we were in the business of trying to catch it. But that meant we had to process every single thing that was going through these companies, which is huge scale for the 4 engineers we had by the end of it. And now I'm currently at Twitter doing exactly the same stuff. Twitter acquired the company in June of 2018. So I'm talking about speed, and I know neither of those animations really made any sense. But in the top left, we have a MiG-15, and in the bottom right, that's an F-86. And I'm sure people in this audience know way more about airplanes than I do. But why I bring these two airplanes into this talk is that they were pretty closely matched airplanes. The MiG-15 was slightly superior, slightly faster, slightly better control. But yet, in the Korean War, the F-86 won the majority of the dogfights it was in. I believe the stat was something like 2-to-1. But it wasn't necessarily because of better pilots. No one really understood why the F-86s were so much more successful. And Colonel John Boyd spent a lot of time investigating this, and eventually came up with this concept of the OODA loop. The OODA loop in military terminology refers to observe, orient, decide, and then act. It's basically a simple cycle that everyone goes through while deciding how to observe what's going on in the field, orient, add your previous experiences to it, finally decide on what to do, and then do it. What Boyd found out was that actually the speed at which you could go through the cycle was way more important than the quality of each individual piece. So with the F-86, due to some small differences, the one being hydraulic flight control and the other having better field of view. The pilots were able to way more quickly observe changes and then act on them, and eventually outpacing the enemy. And this pattern appears everywhere. It also appears in engineering with what is commonly referred to as the iteration cycle. That goes from planning, which may be related to communication, how well you communicate with each other, experience, how well you can make your plans, what you've seen before, generally management stuff, which I'm going to stay away from in this talk because I'm not a manager, and there are people far better suited to talking about that. Going into change, generally how quickly you can change things depends on your programming language, maybe what frameworks you're using, and how much technical debt you have as a company. And finally, the observations, that depends on maybe your tests, maybe your measurements once you've deployed to production, and maybe reviews if you're a mobile app or something like that. And the reality here is each of these steps is much slower for larger companies. Planning takes more time. You have more people and maybe more meetings. Changes, you might conflict with other teams. And finally, observations, you might have more flaky tests and conflicting changes between teams that basically murky your observations. And finally, employee churn also adds up to problems here. This talk is really going to focus on the change portion of this. As an engineer, that's the one I'm really interested in. But before we get into that too deeply, let's start at the beginning. So assuming a brand new company, how long would it take you to build a content management system? By that I mean a simple website where people can sign up, log in, create some pages, and publish them to the internet. Today, you'd probably use cloud and open source, and we really are standing on the shoulders of giants and can do things really, really quickly. 30 years ago, it might have taken weeks to do something like this. You would have had to drive out to a data center, buy a server, install it yourself, maybe set up the networking yourself. 20 years ago, with the LAMP stack, that's Linux, Apache, MySQL, PHP, it got easier, and you could usually run servers online. 10 years ago, AWS was released in 2006. You could get servers in minutes, and maybe using something like WordPress, you could get it shipped out even quicker. And now I would argue a lot of people can do these type of things in minutes. There's lots of new serverless technologies out there. The two I'm interested in are Smyte and Darklang, but they're basically companies that help you deploy your code basically instantaneously. And so there really is this increase in development velocity that's happened over time. And engineers are way more effective with these modern tools. So as a startup, you have your freedom to choose one of these tools and even to change your mind. There's not that much investment in each tool you've picked yet. But as companies age, they get locked down to the choices they made. And they are often very complicated and tend to age badly. And just keeping up for them takes constant investment in their tooling and challenging migrations to move between them. And so you really want to kind of pick the right decisions if you can. And the reality is the decision space is very, very complicated. Supposing you start up with a JavaScript backend, the actual names here are not important, so I'm just going to run through this. But you get access to libraries like React, Koa, Socket.io, but you could also choose C++ or Go, which have their own sets of languages. You kind of want to choose your own sets of databases, but then some databases are also restricted to one cloud or another. And this is probably only 1% of what's available out there, and it's already a complicated mess. Microservices can help you use the best of each language, but again, they tend up getting really, really complicated. And so people tend to want to stick to simpler systems if you can, because each choice incurs a complexity cost here. For every new thing you add, the engineer has to learn the thing. The thing could be a programming language, maybe a database, a dependency injection framework. Whatever it is, the engineer needs to sit down, learn it. Any new hires will need to learn it. There may be unknown issues or bugs with this. So when you're signing up for a new database or a new programming language, especially if it's a new one that isn't really used by the community much, you are likely to see a bunch of bugs. You're likely to see a bunch of issues that you won't be able to Stack Overflow if it's in that category. Finally, it might be incompatible with other choices. So every choice you add means, for instance, if we chose Go in that first slide, We wouldn't be able to use any of the JavaScript frameworks or things like that. And you'll have to integrate each choice with any future choices. And this is entirely true until one of three things. Either you migrate to a new system and you delete all of your old code and configuration. And configuration is also important here. Earlier talk referenced an NFS alert rule that was left over. Things like that will confuse developers in the future and slow them down. So you really haven't completely removed your complexity cost until you've removed every single detail of it. You could simplify your existing system and basically use new technology to remove other complexities in your system, or you could shut down the company and basically delete everything. So how do you make these decisions? Well, time spent waiting for a decision, especially if you're the CTO, you're the lead of this company, everyone else will often be waiting for a decision to be made, and they can't really get any work done during that period, or they might start working on the wrong thing and waste their time. And this is relieved by the fact that not every choice matters the same. So for instance, if you're picking between two compatible pieces of software, usually the choice doesn't matter until maybe later when you need to use specific features of that, and you should decide before switching over. And also importantly here, often it means not using the best tool for the job. So this over here is a $400 juice press. It was actually 11,000 Rand when it was launched. And sure, it's probably the best at making juice, but you could just use a squeezer or your hand for the most part. So the point there is just really weighing the value of these tools. Each individual tool you add to your stack, you really need to weigh the value it brings over the complexity that that tool adds to your stack. I tend to view this a little like this graph. It's hand-drawn if you can't see that the axes aren't straight, axes. But essentially, it's a plot of development velocity against lifetime of the company on the bottom. And over there, I have open source, which I've drawn as this flat line. And now I'm assuming there's this typical company. Perhaps everyone starts out picking stuff off the open source shelf, and you'll start up at the same velocity as open source is moving. And the more you invest in your tools, maybe you can get a little bit faster. But then often you hit this unknown bug. Whatever you choose, you're likely going to have some issues somewhere along the line, which will slow you down. You generally get through it and then kind of carry on. But the thing people often miss in this picture is that open source is continually getting faster. And if you are that company I rendered before, over time, you're going to get slower and slower compared to what is available in open source. And new companies essentially just start further along that line. So as they're starting, they will be faster than you. And so as an older company, you need to continually migrate, continually improve your tooling just to keep up with open source, not to fall behind. And the effect is actually harder the further below the waterline you are, because you'll be spending so much time just getting your tools working before you can actually move forward. If you look at Twitter 15 years ago when it was started, very few of the choices people recommend now, very few of the software that would be recommended existed back then. Some of the software that gets recommended today, Twitter wrote 15 years ago, maybe 10 years ago, but in a lot of other cases, we've had to migrate to the newest software developed by other companies. And that's not a bad thing. There's this huge competitive advantage if you can keep up with that open source line, or maybe even exceed it. But it does take a ton of work to do that. This blog post came out a couple weeks ago that actually speaks to a lot of this in a really interesting way. This guy, Alex Gaynor, basically says, as the scale of a code base increases, so as you add more engineers, add more code, add more complexity, any properties which are not programmatically enforced will tend to regress. So what he's saying here is, even if you trust your engineers, even if you have the best engineers, as you add more and more engineers, more and more code, rules will tend to get broken unless they're actually enforced. And you can enforce these code rules with things like lint, which, for example, looks at your code, looks at the style, and will maybe not allow you to commit if it doesn't follow your style guidelines. But those really slow you down, because every time you get that lint error, you have to go back and fix it, and then push it again. And it slows you down, but it's a trade-off, because you'll end up with higher quality standardized code. There are some things that don't slow you down that are starting to come out, which a lot of people call auto-formatters. But these are programs that basically automatically format your code for you, so you don't have to think about it, which is a great solution to that problem. You could also look at the idea of the monolith here, which people have spoken about earlier in this conference, where monoliths are usually easier to develop. They allow engineers to move faster because all the code's in one place. But the boundaries between services in a monolith aren't necessarily enforced. And engineers will blur those boundaries in order to ship features faster, which is good because you get the features shipped faster, but it's bad because over time your code deteriorates. And so you really need to get that balance quite right. So there really only are two ways to keep up with what's going up in the open source world. The number one is invest in your choice. So whatever you choose, whether it's even building your own software, you really need to invest in it and keep it moving forward. If it's open source, you need to keep it up to date. Otherwise, and open source or your own software, build tooling to support its deficiencies, and maybe enforce good practice. So if there's some part of the language or database that you don't think you should be using, make sure you don't use it. The other thing you can do here is migrate. Sometimes it's clear that the rest of the world is moving in a different direction, and you should just move on. It's not always the easiest thing to do, and sometimes you're stuck. The ideal place to be stuck is with a technology stack with strong open source support, ideally where there are other engineers working on the same problems you are that you're not paying. But sometimes you're not in that boat, and you just have to suck it up and migrate off it. Diving into the investment piece a little bit more, I'm talking about really keeping up to date with the latest stable version. So not necessarily keeping up to date with immediately what's been released, because that'll usually have bugs, but don't fall too far behind, because you'll be the only people encountering the new bugs with different pieces of software there. You want to enforce code style rules. I've talked about this before, but auto-format and lint are great there. You want to clean up old usages. So as you move on new software or you decide new ways of doing things, maybe automatic code modification, manual code modification, or just deleting code can help you there. Speeding up the pipeline is great too. So this goes into the observation in that original iteration cycle, but the faster everything can go, the quicker you can build software. And finally here, improve libraries, frameworks, automatic metrics, anything you can automate that makes developers' lives even 1% better over time will compound and make things way better at your company and help you keep up with that open source rate. As for migrations, it's really just about moving off unmaintained code. So you want to make sure everything you're using has someone actively looking at it, either you or someone in the open source world. If it doesn't, you'll likely, over time, see issues with it. And so you just want to get off it. You should, whenever doing any migration, see kind of incremental value through the migration. I know Silicon Valley has the stat of 18 to 24 months is how long an engineer typically stays at a company. And so any significantly long migration will often see different engineers working on the thing, and often just never completes. And so if you can, at least every couple months, see some kind of value out of a migration, it makes it, A, much more likely that it'll complete, but also useful in the case that it doesn't. There are a ton of different migration strategies. I think that's an interesting talk in its own right, but that's not the talk I'm giving today. The point I do want to make is that you do need to finish the migration. And so you really do pay this complexity cost for the migration until all of the old code is done. There is also a combination between these two things. So since you know you're going to have to migrate at some point, unless you've made all of the correct decisions, which is basically impossible unless you're not building software. So you should really plan escape route. As you start your software, think about how you're going to get off it if you need to. Libraries for feature flags here and double writing, dark mode really help. Dark mode, these things all reference basically abilities to push code into production and then dynamically toggle it maybe on for some users or test the database and see if it works before actually relying on that database. Making sure your code is greppable. So grep is a code search tool. All this is saying is try avoid dynamically generating code. As you dynamically generate code, any future migrations will find it hard to find that code. You might not realize certain features are being used, and it'll make migrations much harder. Clean boundaries between services helps here too. This goes into the monolith story, but actually at Smyte, we started with a monolith, but knew that eventually we would have to pull off a bunch of different services and run them separately. And so we designed them completely separately, but within the monolith, and could later just pull them out one by one as we needed to scale them independently or deploy them independently. And finally, delete unused code, because any unused code sitting in your code base, this falls under all the categories, but any unused code means it's just more stuff you'll have to migrate at some point in the future. And really, if you only have one way of doing things, it helps your life a lot. So I'll be frank, and I know this stuff is fairly challenging, and no one knows exactly what software to choose as you're trying to make the decisions. And I don't really have any exact answers for you either. Picking the right solution is really a combination of what you know, what you can hire for, maybe what the community is doing, a little bit of gut feel. The best thing I can offer you here is some stories, some stuff that we experienced, and some kind of conclusions that we drew out of that. And so this, again, this is from the Smyte days, which was the anti-abuse company. This was when we had hundreds of millions of users, basically social network scale, but we were trying to develop this thing with 4 backend engineers. And adding more engineers would have just slowed us down even more. The first kind of puzzle we had was, and this references the previous talk as well, we needed some solution for our data processing. So anti-abuse system, we've got this single primary event stream. We were providing anti-abuse services for a ton of different social networks, sites like Twitter, sites like Musical.ly, but also for marketplaces. So things like Indiegogo, could have been things like Kickstarter, sites like that. So very, very different websites. We allowed them to send us whatever data they wanted in this single primary event stream. And then we wanted multiple independent consumers of this. So in the beginning, we actually just fed the data in and just held it there. And then eventually we added something that went to BigQuery, which is a massive SQL warehouse that allowed us to look at the data that was coming in and do some basic analysis. And over time, we added more and more services on top of this thing. It only had to be fast enough. It didn't have to be tens of milliseconds fast. Most of our results, because we were doing a lot of processing, were only delivered in a couple of seconds. So that wasn't a strict requirement for us. But we did want to design for migrations, because we knew we would be changing how we were doing things over and over again. And so we wanted the ability to reprocess old data. And finally, we needed something that was extremely scalable. We knew we'd land up processing tens of thousands of events per second. We wanted at least one piece where we wouldn't have to worry about its ability to scale, and ideally not lose data as well. So we were looking for something with at least one semantics, so knowing that if a customer sent us an event, we would process it at least once. In the event of an error, if we processed it multiple times, we would deal with that, but we didn't want to drop anything on the floor. And we came to a decision of using a database called Kafka, which was also mentioned in the previous talk. It's simple and extremely flexible. It's a streaming database. You can stream data in. It stores it, and then multiple consumers can read it out. It could work with any hosting provider, which was important for us here because we had credit from multiple different cloud providers, and we weren't actually sure where we were going to land up. And also, as our anti-abuse system that had this huge scale, we really wanted the ability to get different cloud providers to compete against each other for our business. And so we had to have the ability to move to a different one fairly easily. We needed something with proven scale and funded development, or we wanted rather. The fact that Kafka had been used at LinkedIn, was developed at LinkedIn, and had multiple teams that had engineers that were paid just to work on Kafka was a huge plus for us here. it could handle our spikes, which made the rest of our system much, much easier. So as data flowed into our system, supposing one of our customers got a spike of 100,000 events in a short period of time, that would flow into Kafka, and then everything else in our system would just back up for like lag for maybe a couple minutes. Even a couple hours wasn't the end of the world for the service we were providing. And so by putting all that complexity in Kafka, the rest of our system just had to process events as quickly as it could. And then really as a bonus for using Kafka, they kept adding features that we needed. And this was because we had picked a piece of software that other people were using for a very, very similar purpose. They added timestamps at some point shortly after we were trying to figure out how to do it ourselves. And then they actually added exactly once processing, which we haven't started using yet, but is a very, very powerful feature that will be useful for us. The second database, well, the second problem we had I want to talk about is this countUnique database, which was a very interesting problem for us. As an anti-spam system, we had to answer questions like, how many unique IP addresses has this user used this week? A different question this database could answer is, how many different profile images has the user used? Or maybe how many different URL domains have they sent in their messages? How many different websites have they mentioned? And if they've sent a lot of messages with websites, but it's all been the same website, that's kind of suspicious. This database had to be extremely scalable, though, because we were processing tens of thousands of events per second. Each event would have a couple hundred counters. And so we'd land up with millions of unique sets and hundreds of millions of queries per second. Finally, it also had to be cheap. We couldn't afford to store every single event from every single customer, and so we really wanted some way of summarizing the data. And if it wasn't enough of a challenge already, we also needed sliding time windows. So we really wanted to know how many unique IP addresses have they used in the last hour compared to the last day, last 6 hours compared to the last week. All of these ratios were very helpful in finding abusive actors on the system. The saving grace here was that estimates were acceptable. So if the numbers weren't 100% right, it didn't really matter that much. We were really looking for outliers and giant numbers. Luckily, and after speaking to contacts in a similar business, we came up with this sliding hyperlog log paper. It's a really sophisticated algorithm, very, very clever. The problem was it didn't exist in database form. So it existed in paper form, which explained exactly how this thing worked and what it did, and we knew it was what we wanted, but we couldn't just pull it off the open source shelf. This was still in the early days where we didn't have that much traffic. We knew we would want to scale it, but we needed some kind of solution. And so for our version 1 of this database, we went on to actually every package repository. We didn't care what language this thing was written with. And we found one in Python, this hyperlog log package, which is definitely not the optimal way of writing this piece of software. But using this package, we could write pretty simple code to create these hyperlog logs, store them in Redis, and then expire them after 30 days. And this was not efficient at all. It did work, but it was fairly terrible code, very, very expensive from both a compute power and a memory position. So while we were building this, as I mentioned before, we definitely planned on migrating off it. So if you see the 1 colon in that slide, that is basically just a version number. We, off the top of our head, threw in the value string, just so that we knew that when we eventually moved off this, if we had to move off it, and we wanted to move off it incrementally, we would know which values came from which version of the library or whatever solution we were using. This was incredibly useful because very quickly we had to build sliding version 2. And the reason we had to build this was not actually the reason I thought it was going to be. It wasn't because it was using too much compute time or was too slow. The problem was we were storing it all in memory, all the data in memory, and the data was filled up by this na junk, which is what Python pickle gives you. Reminds me a lot of Batman, but it was causing us a lot of problems. And so the solution here was actually fairly trivial. We just zipped it. And this, we changed the version number to 2. Anything that wasn't zipped, we then zipped. And this actually got us about a year into the company, year and a half. This really terrible in-memory system was serving maybe 5,000 queries per second before it started falling over, which was enough to get us to sliding version 3, which I'm not going to go into, but we did have version 4 as well, version 5. We had version 6. I originally had captions on all of this, which was our sliding version 6, but it would just distract you. It got very, very complicated by the end. But we got there incrementally, relating to the quote earlier in this conference as well, that like it's possible to get to a complicated system starting out with a simple one, but you don't want to go to this complicated mess right from the get-go. Those were 2 happy stories. I've got a slightly worse one for you, which was our event feed. So we needed a key value store with filtered scan. If that's complicated, just imagine Facebook news feed with filters. So for every website sending us all of their logins, all of their signups, all of their messages, events, whatever it is, we wanted to be able to show all the events in a Facebook news feed and maybe filter down to a specific user, a specific IP address, a specific country, something like that. And at that time, we also didn't have a place to store the event data, which we wanted to start storing. So if we could ideally combine these 2 things and store the event data to be looked up by the event ID is what we called it. And it turned out, looking around, this database called React was a very popular choice for key value store. And all the evidence I could find showed it was a great key value store that could scale endlessly and would not cause us any problems in that regard. And then as a bonus here, they had recently added Solr search indexes. So Solr is a very simple search index, open source, and React had added that to their key value store, allowing you to index the data in there. And so this was exactly what we wanted. And so without much deliberation, we decided to decide on React. Long story short, it didn't work out for us at all. The scaling technique that they had used for their key value store did not work well with search indexes. And it turns out some people at Basho actually knew this already. Basho is the company that built React. They knew the search index was a feature that they could sell, but they were rushed in deploying it because the company was running out of money. And months of pain of trying to get this database to work could have been saved by hours of community research if I had just managed to speak to the right people that knew the inside story of this database. I spoke to a friend a little bit too late while we were trying to get rid of it already, and essentially found out that I shouldn't have tried to use it in the first place. And part of the problem here is it was built behind closed doors. So when the company was running out of money, it didn't really appear in their GitHub issues list. And so you couldn't really see what they were doing. But as a saving grace, they were powered by this open source Solr database, which made us an easy migration off it into our own solution. And we eventually did get off it, but it caused us a lot of problems on the way. Perhaps using something like Elasticsearch would have been an option too. We just didn't really spend enough time looking into this decision because we thought there was an obvious answer, and it was a mistake. There's one more mistake we made, which goes into hashing libraries. So while a hash is taking a piece of content and producing a unique number for it, we needed to do this extremely quickly. On each event, we would hash thousands of different pieces of data and use it in different ways. What we needed didn't need to be cryptographically secure, but it did need to have 64-bit output because we wanted to use that in a bunch of places. And so the space there isn't huge, and so a few collisions were acceptable for us. And again, we did some research into the hashing library and came up with this thing called murmur hash. It's a really, really great hash function. Nothing wrong with the algorithm of choice. The problem is we didn't spend as much time researching the implementations we used. And so we went onto the JavaScript package library and pulled the first Murmur hash implementation we could find off. And it turns out that that library author hadn't actually read the spec at all, for the most part. They had just pulled it off and implemented it. Murmur hash has some really nasty complexities, which I only found out later once this bit us. It has a 64-bit version and a 32-bit version, and they have different hash outputs for the same function. And so because they're optimized in different ways. And so once we had started using the wrong one, it became very, very difficult to switch to the correct hash version. And then on top of that, the JavaScript library was hashing the UTF-16 bytes that V8 stores inside itself. And so it made it basically impossible for us to move to any other microservice. We had to keep this code in JavaScript because we had to keep using this hashing library. So as a summary for choosing software, there's not always a clear winner over here. You really need to invest in migrations, make sure it's easy to move off of choices you've made if you can. You should check if the team's funded. Funded teams are always great, and ideally, if they're developing with the community, that helps a lot too. Get some kind of sense for the quality of the engineering. You never really know what's going on behind the scenes, but definitely double check the code before you actually pull something off, especially if it's not used by the whole community already. How big is the community? Check more popular software. Even though it's not the best software often, the fact that you've got more people using it means the answers will be on Stack Overflow. And so you can just pull that off. But that's only if you have the same use case that the software is being written for. And then finally, sometimes it actually does make sense to build these things yourself. But that's not the common case, and you should avoid that when you can. So again, back to the beginning. Engineers are more effective with modern tooling. And so whenever you add these tools, you carefully consider the value they're giving you for the added complexity and not add too many things. Using tried and trusted community software is just better in general. One good tool is better than 10 perfect ones. Invest in making your tools work better for your engineers. And if the thing you're using isn't good enough, just migrate off it. So I want to back this good enough thing because you don't always have to have the best piece of software. It doesn't just need to be good. It needs to be good enough. Something you can understand is way, way more powerful than any complicated piece of software, and especially if it's got some community backing. Thanks for listening. I have some of those stickers outside. That's it.